Good evening again. Velocity and acceleration are both vector quantities. Recall that vectors have both magnitude and direction. An object traveling at a constant velocity, therefore having no acceleration, does accelerate if it changes its direction. So turning the steering wheel of a moving car makes the car accelerate because the velocity changes direction. Virtual physics, the moving man. With this animation, you can produce both variation of acceleration and velocity shown in figure 3.2, plus a few more variation. Vary the velocity and acceleration by sliding the red and green markers along the scales. Keeping the velocity marker near zero will make the effect of acceleration more obvious. Try changing the acceleration from positive to negative. While the man is moving, we'll come back to this animation and look at the chart's view when we study graphically representation of motion. Click to view content and achieve check. Which part A or B is represented when the velocity vector is on the positive side of the scale and the acceleration vector is set on the negative side of the scale? What does the car's motion look like for the given scenario? A. Part A. The car is slowing down because the acceleration and the velocity vectors are acting in the opposite direction. B. Part A. The car is speeding up because the acceleration and the velocity vector are acting in the same direction. C. Part B. The car is slowing down because the acceleration and the velocity vectors are acting in the opposite direction. D. Part B. The car is speeding up because the acceleration and the velocity vectors are acting in the same direction. Calculating average acceleration. Look back at the equation of average acceleration. You can see that the calculation average acceleration involves three values: change in time, change in velocity, and acceleration. Change in time is often started at a time interval, and change in velocity can often be calculated by subtracting their initial velocity from the final velocity. Average acceleration is then simply change in velocity divided by change in time. Before you begin calculating, be sure that all distance and time have been converted to meters and seconds. Look at these examples of acceleration of subway train. Word example: an accelerating subway train. A subway train accelerates from race to 30 km/h in 20 seconds. What is the average acceleration during that time interval? Strategy: start up by making simple sketch. V initial is equal to 0 km/h. V final is equal to 30 km/h. Acceleration is equal to how much? You can see the y direction and the x direction. This problem involves 4 steps. 1. Convert to units of meters and second. 2. Determine the change in velocity. 3. Determine the change in time. 4. Use these values of calculating the average acceleration. Solution: 1. Identify the known. Be sure to read the problem for given information, which may not look like numbers. When the problem states that the train starts from rest, you write down that the initial velocity is 0 meters per second, therefore V initial is equal to 0, V final is equal to 30 km/h, and change in time is equal to 20 seconds. Convert the unit. 30 km per hour times 10 to the power of 3 meter divided by 1 kilometer times 1 hour divided by 3600 seconds is equal to 8.333 meter per second. Calculate the change in velocity v final minus v initial. 8.333 meter per second minus 0 is equal to plus 8.333 meter per second, where the plus sign means the change in velocity is to the right. 4. We know change in time. So all we have to do is insert the known value into the formula for average acceleration. Discussion. This plus sign in the answer means the acceleration is to the right. As you can show in the above, acceleration is equal to change in velocity over change in time. 8.33 meter per second divided by 20.00 second is equal to plus 0.417 meter per second square.